So before we start with the new stuff or not so new stuff, just a comment on what has been raised on Tuesday regarding the convergence of this so-called Neumann series of the operator. So for the T matrix, we had this expression as an infinite series of terms, and it was rightfully asked that when does this converge and when can I rewrite this or treat that as a geometric series, and I said naively and very stupidly that I can do that formally anytime. So what I need to be careful about is that those are operators. So it doesn't make much sense to talk about convergence without specifying, okay, on which momenta do I worry about convergence of that series, and what kind of interaction do I put in? And the convention is that usually one considers this series for localized, not local, but localized potentials to a certain area in momentum space. And the typical assumption or class of interaction potentials one considers has the property that V of K is usually less than 1/1 plus the magnitude of K times power of 1 plus some, and I use the notation of Fadeev beta, and then some constant here. So these are the typical potentials one considers. They have this, and for those you'll find a huge class of realistically encountered potentials in nuclear, particle, and whatever the atomic theory. And if one imposes or only considers potentials which fall into that category, so they have a certain fall of behavior for K going to very large values, you can find that all those terms here obey also certain, so I don't recall the exact inequalities, but then you get conditions on A, V, G naught, V, and I write this just symbolically to the power of n, K prime. But this is also bounded by some upper value m. So, and that m is dependent upon K prime and K. So you can sum this for, an interaction strength and momenta below a certain threshold such that this series converges. So, and the mathematical details are something I can't produce on the spot, but this is the thing which, it's not automatic that this converges, or it doesn't even make sense to speak of that. So the fact that you can sum this operator series formally is fine, but it doesn't tell you whether the result makes sense if you apply it to a certain set of potentials or momenta or in the external states. So this just as a theta should be larger than 0. So this identifies those potentials for as soon as theta is larger than 0, so meaning not necessarily Coulomb, you can find this inequality. So it's just a positive real number. Yes. So it's not the academic quarter, but the academic 2/3 quarter. So I wasn't aware that my story on Tuesday was that confusing, such that the audience came down to a very elite group of people. So I'm sorry for that. So I tried, I was, yeah, so I was aware that it was a bit technical, confusing, and chaotic. I want to not spend time in recapitulating that, but I want to start from a different point, end up in the middle of the lecture at the same state where we left off at the end, namely the kernel or eigenvalue equation for the three-body bound state, but reach there via a route which is generalizable, if that's a word. And this is also the point where the connection to particle field theory is easily made, I think. So it should be much more entertaining or digestible today than it was on Tuesday. So, and in that spirit, the starting point shall be the green operator. So this is an object which we are, or you are more familiar than I am in dealing with quantum field theories. In this context, this should be a function of the energy Z, or an operator, the inverse of that object. So energy minus the Hamiltonian. And this is where we can make or feed in all the knowledge we gained through the other lectures, namely the Lagrangian-based EFTs, non-relativistic ones. So these give me a certain Hamiltonian, and that operator is what I incorporate here. And through that, I define the green operator. And from that operator, I can go on and calculate whatever I want. So this is not something I want to review, but the spirit is that this is a very, that is the most powerful quantity in, not the most powerful, but amongst the most powerful quantities. Once I know that, I know everything. So I can calculate cross sections, or before that, I calculate the S matrix. So this is why this approach is so appealing, because it's in that sense universal. I only need to concentrate on one quantity. Once I know that, I can extract all the information my theory gives me about the physical world described by it. So, and this operator is something which, is a function of an energy, complex, real. And the spirit of this Fadeev decomposition we alluded to, Daniel ended up with, and I used at the beginning of last lecture, was that one does not need to consider the entire green operator, but rather you decompose this, this operator into certain pieces. So into various components, let's call them K1 plus K2, and so on. where for certain energies where I'm interested in, so if I'm considering my physical system under investigation at a certain energy, and I decompose my operator such that one of those components becomes dominant for that energy, for that Z, while all the others are insignificant for that purpose. So this is the idea of this Fadeev or all the other decompositions. So I simplify my problem. I don't investigate the entire Green's function anymore. I only concentrate on that part or that component of it which dominates at this energy. So this is, in my understanding, the idea behind all of what we are doing. And this is what I want to do now and end up at the same point where we arrived last time. So if we do that for the purpose of describing three-body bound states. So this was the object of interest in this investigation. We wanted to investigate what happens to a three-body system, a bound three-body system, if we take the limit of the coupling strength of the interaction, which we build with our EFT, such that the two-body system develops an infinite correlation length. So what are the dominant components for that task? So, and the components we can, and now I'm getting diagrammatic, so I think this is intuitive for most of us, or for you more than for me, but at least I can speak of those different components in terms of how the interaction connects certain pieces of the system. So I can identify a free component where, so I'm now confining myself to 3 particles. If I have enough time in the end, that was an experiment I wanted to do for today's lecture, so that this is also a bit a constructive demonstration that we do it now for 3 particles. In the end, I haven't jotted it down myself. I read about it a couple of weeks, months ago, but in the end, we want to apply the same logic for 4 particles and see if that is something you could do as well and apply to maybe a different problem. But let's stick now to 3 particles in the external state. So the state this operator acts on. So I have 3 particles. The diagrams are understood such that you have an incoming set of 3 momenta, an outgoing set of 3 momenta, and one possibility of that transition is that nothing happens at all. So all 3 particles propagate freely through, and that is one of the components I'm looking at. So this is certainly a component which is important if I'm considering the scattering of 3 particles at a positive total energy Z. So a different class of, a different component would be the one where I have a bound system of 2 particles. And wait, did I want to decompose it like that? No. I disconnected. This is not. So where I consider a bound system of 2 particles and a spectator particle which is detached from that. So this is another class of processes which can unfold, and this, another piece would be that. And just to make the sketch less convoluted, I need to, so then I have the possibility that I have in a bound state for particles 1 and 2, 2 and 3, and then 1 and 3, and 2 as a spectator. So this is another class of all the possible processes I can, or which are included in G, namely that the only case where the interacting part of H goes into effect is between particles 1 and 2. And there this blob resembles all possible interactions I can have. So this blob is now my, basically what I wrote down here, this T matrix. So I can have one interaction between particles 1 and 2. I can have two interactions with a free propagation between all, amongst all the particles, and so on and so on. This is something you already calculated and we spoke about last time as this T matrix in one of the subsystems of this three-body system. So these are a second class of processes incorporated in that G. And the last one is the one where all three of the particles are connected through an interaction. So in this last class, all only diagrams like, or processes where I not only have in this series one type of interaction, but possibly two. So I have 1, 2, free propagation, and then 2, 3. So this component, if it comes out, so these are lumped into this last large blob, and that would correspond to my process here. And again, those wavy lines are not photons, they are placeholders for whatever interaction I'm considering. It might be a contact interaction, it might be anything which ties together particle 1 and 2, and later on 2 and 3, or the other way around. First 2 and 3, and then 1 and 2. Okay, so more symbolically, so this is my G0. So G0 is the part of the Green's function where this H is replaced by the free Hamiltonian for the entire system. And then I write this as a K Ij G Ij and a sum over those pairs Ij. So this is just notation for the moment. So these kernel functions Kij are defined as V0 V Ij. And so the reason why I'm doing that becomes clear in a second, because that's the procedure I can follow then for whatever system I'm considering. I do the same thing here. This I write as or I decompose, I factorize into component I times the Green's function plus. So what do I want to do here and why am I doing that? Again, the goal of this procedure is to isolate the simplest structure from the Green's function, which carries information about my system. So the expression we derived on Tuesday, I don't know if to me it was already extremely complicated as an object to manipulate or to gain information from analytically. So, and nevertheless, you can do that. If you don't focus on that part of the Green's function, which is the simplest one, this whole hope is futile. You might not get anything out of those analytical expressions at all. So that's why I want to isolate the simplest structure, which there is hope that I can tackle and understand something analytically from it without having to rely on heavy numerics, which gives me out in the end a number without any understanding what the phenomenon is all about. So that's why I further decompose this so-called connected piece of the Green function into an irreducible piece times all possible diagrams. So again, here what appears is the full Green function, which I had already, which on the left-hand side of the equation. Here, I do something very similar, but for the subsystems. So here, what I'm looking at, or what I split the individual components into is an irreducible piece, and I define what I mean by irreducible in a second, of the subsystem times the full Green function in this subsystem. And again, this is a procedure you can then, or what we want to generalize eventually, but in this language, it becomes very intuitive. So I always take the full Green's function, then I take subsequent subsystems in which I then identify irreducible pieces. And now that I'm using this term all the time, so I'm not sure if there's a deep connection to group theory, but in terms of diagrams, an irreducible set of diagrams comprises all those diagrams which connect a certain subsystem such that if I cut or remove the rightmost diagram, it falls apart. So that is something which, so what are examples for this irreducible diagram? So this definition, I won't write that down because it becomes clear if I give you some examples. So for 3 particles, this is an element of that irreducible set. So if I take away the rightmost interaction or piece, then it falls into 2 separate disconnected pieces. This one is not part of the irreducible set. If I remove the rightmost thing, the diagram is still connected. The reason why I'm doing that is, again, to find the simplest diagram, which still retains the information about the process at energy Z. Okay, the same logic applies here. So here it's easy. Here I also identify for each of those components, I identify those irreducible components in the subsystems. So in this case, Kij is the irreducible diagram, and this is easy for two lines there. This irreducible set is just one interaction. So that's the only thing I can see which falls into disconnected lines if I remove that. All other diagrams are, in that sense, non-irreducible or reducible. Okay, so now, again, you can analyze all of that mathematically and rigorously where the various diagrams here become relevant. Maybe to connect that to the all present bubble sum of two particles, what I have here is I have this irreducible piece, and then so don't take this too literal. I multiply that with all the green diagrams in the subsystem. So this operator here is, so I haven't defined it rigorously, but so this is G naught, and then Gij. So there is no, so and so those green functions are defined with the Hamiltonian, which acts only with, which comprises or includes only those interactions for the subsystems. And again, this logic is generic. It's not exclusive to the three-body system or to two-body interactions, 3 or 4. This is always the case, and whatever I'm telling you now, you can translate or understand as, okay, I decompose my green function such that I consider all the possible fragmentations of my n-particle system into various subsystems. And for each of those subsystems, I factorize the set of diagrams into one of those irreducible pieces and the green operator, which describes evolution in that subsystem only, while not doing anything to the other particles of the system. So in this Hij, I still have a free part which describes the evolution of the spectator particle or particles in larger systems. Yes. Right, right. Mm-hmm. Oh, no. It's not G12. So G12 also includes the free evolution of 1 and 2. So G1, that's the difference.
Typically some X, then this guy, you are calling it K, right? This diagram,
yeah.
Single diagram is K. The first diagram for that is K.
Mm-hmm.
Did you?
Yes, in that case. Yeah. So it's.
Isn't there a recursion relation?
Yes, yes.
Like plus A times G, right? So G or X equals to K plus K into X, something like that.
Yeah.
So, I guess the base multiplied by right? Then you get rho B, and rho B, right?
So there are in this in this business of decomposing the wave function, you can replace all of those objects here with your favorite operator. So you can introduce a P operator, and whatever. This is, I think and this is a choice which is, again, in my understanding, I haven't applied it to many problems, but to the ones I looked at, this approach, I don't need to invoke this notion of a T matrix. But it becomes very handy in different circumstances, and this, but yeah, you're right. So I can reformulate that by including the respective dynamically equation or Lippmann-Schwinger equation for G, or that is. So what is important to me is now that one has an understanding of for which processes are those various terms now relevant. And what we analyzed last time was, so we are interested in bound states, and for bound states, it is this, only this piece, which includes and encodes all the information. Those pieces here are of importance if I'm interested in 2-1 scattering processes. So if I have, if I want to consider S matrices where I have an incoming pair, so if I always consider two fragment scattering events between a so-called dimer or a deuteron and a neutron or proton. And I have the same in the outgoing states. So if my S matrix is always, so this scattering described by an S matrix dimer plus neutron and dimer prime plus neutron prime. If I want to consider, if I go to, all of that is a bit hand waving, but I think it's a good intuition you gain. If you, so this introduces certain thresholds. So below a certain relative energy between D and N being or identifying a certain region of Z, there is no way that the system breaks up. So if I'm only considering energies which are from minus the binding energy of the dimer up to 0, I don't need to consider breakup reactions into 3 particles. As soon as I enter this different regime of energies, I also have to include in my S matrix processes which are evolving into those diagrams here. So then it does no longer suffice to only analyze or include in my calculation those ones. I also need that. But in any case, these here entail the possibility that the third particle is found infinitely far away from the dimer, which is something which contradicts the notion of a bound state. So for the bound state, I always need to look at this object here. And here, I only write down what is the case. And if you don't come up with an answer until tomorrow morning, and you don't ask me tomorrow morning, then I will not prove it. But the condition is that the bound state, and now I'm being a bit more explicit, is an eigenstate of that operator I here, evaluated at minus the binding energy of that state, and the eigenvalue corresponding to that state is 1. So this is, and here you see if you are able to derive or to motivate that equation, you see that you would have done a lot of unnecessary additional work by considering the entire set of diagrams as a function of Z, and then maybe find poles at minus the binding energy. All one has to do in order to find bound states non-relativistically is by considering this eigenvalue equation. Okay, and so, but just to make that, so this is true for the A-body system. So even if I formulate this decomposition for more than 3 particles, this always holds true. So the A-body bound state always satisfies this eigenvalue equation where the kernel or the operator is comprised by the set of irreducible diagrams for the A-body system. And that is an enormous simplification compared with the entirety of those diagrams. So in the simplest case, let's see if that holds true, or if we made a very, or if not I told you something ridiculous. So does all of that hold for the 2-body system? So for the 2-body system, I can write down this irreducible operator immediately. And I should also find an equation I recognize from, from what I did in my kindergarten quantum mechanics. So that means in the 2-body system, did you have enough coffee to tell me what I is? So G0 V. Yeah, so if I'm considering a 2-body system, so if that is true, what should be the case is G0 V times psi is psi. Is that something we believe in or not? So it's, yeah, we do. The only thing which is, I think, worth commenting about is that minus B minus H0 minus 1 V psi. That this object here, we always, or sometimes we always write those green functions as functions of complex energy in order to avoid the ill-defined character of that on the real axis. This is unnecessary here for bound states because the energy is smaller than 1. The eigenvalues of H0 are positive, so that object is always well defined. And here you see that, okay, indeed, if psi is a bound state, it satisfies the Schrödinger equation. If you multiply on both sides with that one, then you just get what you want. So this is for the simplest case where and this is then the embedding of that bound state or this system into the larger system. For the but I haven't used the, so this is, you get this just by invoking that and knowing that, or postulating that the bound state obeys this equation. This is how we got to the Schrödinger equation. Yeah, so, okay, let's say, so I is the, is a set of irreducible diagrams. So let's, so I make another example and then you tell me if that gives you that intuition which you're aiming at. So diagrammatically, what is this I? So this is now not equal to C. What is that? So in words, the I, I'm hanging myself, corresponds to the set, the set of diagrams of which, if you cut the rightmost interaction, you get a disconnected set. So this is the formal definition, which I think, so all of that is based on a, so all the terminology is based on a paper by Weinberg, which I think has been distributed as a set of reading, but if, okay, yeah, that's, but that's the definition. What does that mean? So, again, the blob resembles all the connected pieces of those two. So this is one of the options, particle 1, 2, 3. Another component of that irreducible set is if I have that, and another one is that. Now, 1, 2, 2, 3, 1, 3. Yes. What is missing? So if I put the blob to the right, I will not get disconnectedness. So the blob is or let's write the blob more EFT-ish. So this is the blob. So now each of the vertices corresponds to one of those lines. And if I put that to the right, it does not disconnect. This is, but so I think you can formulate all of that by defining irreducibility as cutting on the left. Or so that is something I think can be done.
Somewhere in between, you have another point.
So meaning I have that, then I have this, and then like that, or so anything here. Yeah, so it's legitimate, but if I cut that, it's still connected. So it is part of the it is part of C, but not of I. So this graph comes from flunging this G onto it. So this cut the rightmost. C sums up or is the set of all graphs which are connected in any way. So and from in that set you have I. I is a subset of that because G includes the repropagation, but it includes all other connected pieces as well. But irreducibility is all I need to consider. So I don't, and this is, so we get finally to the end of the recap soon. So, but there's still something missing here, I think, because, yeah, so what you should have raised is, there's another diagram here, which is irreducible, where I have, so I interchange these two lines, just the labels, and then I have an interaction between 1 and 3. So the subsystem interaction is still the same, but it becomes a bit awkward in the in writing in drawing the diagram. And the same thing you have here for those where 1 now goes with 3 and 2, and here 1 goes with 2, and the subsystem is in 2 and 3. So, but this is because my interaction is V12 plus V23 plus V13. Most of the examples in the literature which demonstrate this this procedure just do the discussion for only 2 pair interactions. And this is where you still get most of the features out and you don't have to worry about these additional diagrams or the awkward paintings. Okay. Evolve. So yeah. So so GZ includes all diagrams. I includes those diagrams. So let's make this C. And what we have is we multiply this set by G. So let's take a subset of G, a very small subset, which is G0, plus an interaction between 2 particles, plus an interaction between one pair and a different pair. Now, that one combined with all of those gives you the identity. So if you're not familiar with or fluent in that language, why is this the identity on those diagrams? You insert a complete set of momentum eigenstates. This gives you here delta functions. So you end up with the same matrix element here as before. So those are to be understood as matrix elements. So you have, and in a certain representation. But this is something I feel you are better at than I am. So those diagrams in momentum representation there, I have a E1 prime outgoing, E2 prime outgoing, E3 prime outgoing. And with the condition that the whole evolution in here happens with G naught at a certain energy, Z. So, and this notion of off-shellness then refers to whether or not the total energy of these external states is equal or not equal to Z. So this is that. If you take the product with a different state here, you get something else. So if you take this one times that one, the matrix element to evaluate is that one. But now I think I lost what your problem was. So this is reducible. Yeah. Kernel times I0. These are the only irreducible pieces, those 6. This one, no. This is not an irreducible diagram. If I cut off that, it's still connected. The definition of irreducibility is that if you remove the rightmost interaction, and this is a definition which is useful or practical, don't read too much into that, but it isolates or it identifies a certain set of diagrams which encode all the information about the bound state I need. But if you have, so this diagram here is not much more, but is more complicated than the ones in the irreducible set. If I remove that, I get an irreducible diagram. This is maybe the confusion. Okay, so now let's connect that to what we've done on Tuesday. And that is now quite a nice thing to realize. So thank you for making me write down the irreducible diagrams for the three-body system because that's what, yes. Fifth from, yes. So, yes. Yeah, so here it should be 2, 1, 3. Yeah, right. And that should be wait. This should be 3, 2, 1. Yeah.
Is the same, so that remains 1.
Right.
Except that only changes fraction with 3 instead of 2, unlike the top.
Yeah.
That is what.
But this is so I so here so I just don't want to do the same thing twice. So let me finish the story. So this is something you can sort out. This is not rocket science. None of that is. But now that let's use that to get to the point where we stopped on Tuesday. So we want to find the bound state, and we want to find an equation which we can analyze. So these objects there acting on a wave function, so I write this symbolic. So we know that these pieces here are the T matrix in the subsystem, G naught times the interaction between the other two particles. So you write this now as, so this here for A equal to 3, we get a sum over, and now I hope I don't ij v a. So is this, so k vk so this is a bit a 3 particular notation that ijk are different numbers, so those are all permutations of 1, 2, 3. And Vk corresponds to the interaction between the particles which are not K. That, and here I sum over, yeah, whatever it is, I, J, K. This acts on my psi, this equal to psi. Okay, this is what it is. It's a connected diagram now through that sum. Not through the sum, through that V. Now, so I've already mentioned a particle identity. Thus far, the discussion was, and I haven't stressed that at the beginning, on possibly distinguishable particles. So the system, or the very peculiar system we are looking at, is a system where the energy goes to 0, and it's a system of identical Bose particles. So in that case, you can, and again, I won't do the algebra for that, you can express each of these terms in terms of the others by applying certain permutations. So permutations don't do anything by definition to a system of identical particles. So what I'm ending up with is that this equation simplifies to a sum of, not a sum, to T G naught, then a sum over permutation operators times psi. That was my excuse for not joining you for dinner last night. So this argument, this operator we haven't looked at in, or we haven't seen in this Faddeev equation, which Daniel wrote down in the end in this matrix equation, if you remember. This operator we have. This was exactly the operator which we analyzed and derived in momentum representation at the end of our lecture. And now we see how, or I hope you believe that those steps are doable in a finite time, where I'm now ending with just the logic, but we ended Green's function object. We isolated certain pieces which were relevant, dominant in certain energy regions. And at those energy regions, namely smaller than 0, which are relevant for the bound state of the entire system, we ended up with, for a system of identical particles, with the same equation which we obtained, or which we started from. But the benefit of all of that discussion now is that, speaking of irreducible diagrams, decompositions into disconnected, connected subsystems is not something exclusive to 3 particles. So this is something we can do now for the n-particle system, and whether or not we can find pieces which are as easily analyzable as in the 3-body system, that's a different issue. But at least we have a recipe for the analysis of, or that part of the Green function, which is the bare minimum to encode bound state characteristics. Oh, I still have time. Haha, great. So in our case, that was, so these operators here, if you write them out, so I left it here like that because this is still general. So what changes in the larger systems is, in the larger systems of identical particles, is what the sum over the permutations is. But you're right. I mean, in our case, this set here was the sum was equal to P12, P23 plus P12, P13. So now comes the ugly equation, and I'm not sure, so I won't get to the other thing which kept me awake last night. But at least I hope that this is something which we can discuss very quickly on tomorrow morning. Namely, so now let's specify, or all we did last time was to write down this equation in momentum representation. And in momentum representation, what we found was that this now not psi, but again this this amplitude of psi E minus E squared minus U squared M U. So it becomes the equation becomes easier if one considers this ansatz for the bound state wave function in terms of an amplitude in the numerator, and one factors out this denominator, which corresponds to the to H naught going on the free particle state. So this P then obeys an equation 3 prime U lambda times T or T minus Q applied to phi so this is now feeding this wave function, or first expressing this eigenvalue equation in momentum representation, and then, or rather this ansatz in that context, and then the ensuing equation is that one here. And the kernel, or the operator whose eigenvalue spectrum we are now considering, is that one here. Or all the information, so this is to save me time for tomorrow. I will not write this down ever again. But what I will use is that this is now a function of E prime, the energy, and the two-body coupling strength, or equivalent to that, the two-body scattering length, correlation length. So, and I denote that to be consistent with the original derivation of that as G. So G is the coupling strength, E is the energy, and which appears here in the two-body off-shell amplitude. And so off-shell in that sense we discussed before, and the two momenta. So yes, and I will be much more efficient, or no, we have been efficient today, I think. But so I will keep the analysis of that three-body kernel very short, but not to forget the essential steps. And then we'll end up tomorrow with the, with more EFT in the view body sector. Questions? This is that. This is, so it's a function of the energy. And the energy is not the energy of the total system, but shifted by this energy of the spectator particle. So this comes about through that peculiar choice. So P is the momentum within the pair. So this is the two-body amplitude. And the P refers to the momentum between the particles which are within that pair. And the reason why there are always this three quarters is that you have the reduced mass in a equal mass three-body system, and this object here is the kinetic energy of the spectator particle. Should be. Yes. Yes. Sorry, this is a bit, so it goes out of that equation. It's you can write it out of the integral. Yes. So this is the only part where the coupling comes in. Those U's are the vertex functions, so they do not necessarily appear if you're choosing a renormalization scheme where which does not use cutoff functions, and then all the stuff goes into that G. But this is one of the differences. So if you read the original derivation of that, they go into a lot of effort to justify the splitting of, or to split that integral here into a finite piece and a UV divergent piece. So this goes from momenta here, go from in magnitude from 0 to infinity. And that, if you don't do anything, diverges. For EFT interactions and amplitudes, where this G becomes a floating parameter with G such that I'm always enforcing finiteness, this is not a problem anymore. So you do that regularization at an earlier step. So this is not something which is formulated rigorously. This was one of the reasons I picked that, because I think there the traditional derivation and discussion benefits from this field theoretical renormalization procedure where you make sense of the infinities by defining floating coupling constants. And this connection wasn't there at the time. If not,